guys, my name is Nako Nakatsuka. I'm a fourth year chemistry PhD student at UCLA, and today I'll be helping you guys out by going over some general chemistry concepts. And good luck with the course. So now I wanted to move on to talking about the basic rules of drawing resonance structures. So these are the fundamental rules for drawing any structure. So the first rule is to shift one of the lone pairs, which I'm going to abbreviate as LP, on an adjacent atom down to form another bond. So this is the arrow pushing that I showed you before, where you shift one lone pair on an adjacent atom down to form another bond. The second thing is shifting one of the bonds, can't spell anymore, in a double or triple bond up to form a lone pair. So that's also something I showed you based on the arrow pushing. And then 3, draw additional resonance structures and excuse my abbreviations, but hopefully you can figure out all the abbreviations that I'm writing out. Draw additional resonance structures by repeating steps 1 and 2. For each adjacent atom with a lone pair. So every atom that has a lone pair can be arrow pushed to form another bond. So as an example, if I have this molecule, which is the formate ion, HCO2-, it has a carbonyl right here, and then it has a hydrogen here and an oxygen here. So straight off the bat, by looking at this molecule, you know, okay, this probably has a resonance structure. Why? Because there's lone pairs on the atoms, and there's a double bond, and there's single bonds. So, okay, this lone pair on this oxygen can move to this bond, and this bond can then be broken, and a lone pair can be pushed onto this atom. So this has another resonance structure with this form. So as you can see, I switched the single and the double bond position. And if I wanted to switch it back to this, I would go lone pair to this bond, in turn breaks this bond, becomes lone pair. So it's the very straightforward process of shifting the one lone pair and then shifting one of the bonds. So now I want to talk about 2 exceptions. As is with all chemistry topics, there are always exceptions to the basic rules. So fluorine is one of them. So fluorine is very unlikely to form 2 bonds and 2 lone pairs, since it would have to lose an electron to do so. But if you remember looking at your periodic table, and if you remember the electronegativity trends, fluorine is the most electronegative element. Thus, it would very much not like to lose an electron, so this is very unlikely to happen. So fluorine does not participate in resonance. As an example, let me draw you this picture. If we have CH2, and then a double bond to C, fluorine, and then a hydrogen. Let me draw out the lone pairs on the fluorine. This fluorine could potentially, following the rules that I wrote above, shift these lone pairs onto this bond, and then this bond would be shifting lone pairs onto the carbon, right? And so in theory, you would think that this structure exists. However, fluorine right here does not like to have 2 bonds and 2 lone pairs. This structure is actually not possible. So fluorine is an exception to this rule, and this structure is actually the only one that can exist. And this is the correct structure for this particular molecule. So fluorine is one to take care of because it's an exception to the resonance structure rules. Another exception to the rule is oxygen. So oxygen is very unlikely to make 3 bonds and 1 lone pair, because in that case, it would have to lose an electron. And oxygen is the second most electronegative element. So you can see the trends, right? Fluorine is the most electronegative, oxygen is the second most electronegative, and thus both of these guys don't want to lose any electrons and create the resonance structures. So as an example, I can squish one in right here. If I have this structure, you would initially think, okay, I can shift the lone pair right here to this bond, and then I can move up this bond and create a single bond. And you would go ahead and draw the resonance structure, which would look like this. However, if you look at this oxygen right here, you would see a red alarm going off because oxygen does not like to make 3 bonds with 1 lone pair. So this structure again is not possible, and it is not a resonance structure for this particular molecule. And this is considered the best because oxygen likes to have 2 bonds with 2 lone pairs like so. I want to summarize the things that I just said based upon this simplified formula, with X double bonded to Y, single bonded to Z with a lone pair. But there were a few things I wanted to mention, 4 to be precise. So Z can have more than 1 lone pair. This is just an illustration of what this particular molecule could look like. X and Y can also have lone pairs. The X and Y bond could also be a triple bond, and the Y and Z bond could also be a double bond. So this is just a particular example. However, Z cannot be fluorine with 1 bond and 3 lone pairs, and it can also not be oxygen with 2 bonds with 2 lone pairs. So now let's talk about benzene very briefly. So benzene shows that it's possible to have resonance structures in ring formations, and benzene in particular has 2 resonance forms. So as you can see right here, we have the double bonds like so, but I can actually shift these like so and end up with this resonance structure, which again, if I wanted to get back to the original, I could just shift these bonds. And benzene, as the resonance hybrid form, is often drawn with a circle in the middle. This is an alternative to drawing it out like this. Since all the dotted lines take a lot longer than necessary, people often draw it as a circle, and that's something I wanted to show you guys in case you came across it.